Unit 2, Homework 2. Now, my questions are probably in a different order than yours, and any numeric questions may have different numbers. So I will show you the technique, and then you will need to apply it to your situation. My number 1 asks how many milliliters of 0.200 molar HNO3, so nitric acid, should be added to 209.0 milliliters of 0.00666 molar 2,2' bispyridine to give a pH of 4.02. We're going to use the Henderson-Hasselbalch equation here, but we need to know what the pKa is. Now, I have started this Ka table of values, and most of it is occupied by a table of values produced by ChemLibra texts. But as I come across things that are Harris specific, I will be adding them to the top. Now, at the top is this 2,2', and I spelled it wrong, but bispyridine conjugate acid. So the bispyridine is a base, and its conjugate acid has a pKa, which is what we need for the Henderson-Hasselbalch equation, of 4.34. Now remember, with the Henderson-Hasselbalch equation, we have pH equals pKa plus the log of the base over the weak acid. So here we have 4.34 here. Our pH is going to be 4.02. So when we say we have 209 milliliters of this amount of my bispyridine, what I have is this is the amount of base, not of acid. So what I have is this bispyridine complex plus hydrogen is going to be in equilibrium with the conjugate acid of the base. Now the bispyridine, the moles that we have, I'm going to take my volume, 0.209 liters, and multiply it by my concentration, 0.00666, and I get 1.39 times 10 to the negative third moles. And I have some amount X, I don't know how much yet, okay, of my hydrogen. Now I'm going to be shifting this amount, these moles of bispyridine, by that amount X. That is then going to force my hand with this conjugate acid. So the base then becomes 1.39 times 10 to the negative third minus X, where the weak acid concentration is this value X. Okay, this is not only being able to apply the Henderson-Hasselbalch equation, but understand where these values come from. So now we need to do some algebra. So 4.02 minus 4.34 gives me a negative 0.32, which is equal to the log of this ratio, 1.39 times 10 to the negative third minus X over X. I take the anti-log of that negative 0.32 in order to get that ratio by itself, so 0.478, and then I have more digits. They're going to stay in my calculator, over X, 1.39 times 10 to the negative third minus X, multiply both sides by X, get our x's, collect our x's, so we're not going to multiply. We're going to add x to both sides, so this becomes 1.478x. Now I'm going to divide both sides by this number, and I get, let's see, 1.39 times 10 to the negative third. And I get an x value of 9.400 times 10 to the negative fourth, capital M molar. What does that x represent? That is not our answer. Well, that x represents the moles of acid that were added. So if I have, there, that's better. If I have this number of moles of acid, then I need to use the concentration that I was given, and it's per liter. A liter is 1,000 milliliters. We were asked for milliliters, so I'm just going to put my 1,000 there. And it's 0.200 moles of that acid per 1,000 milliliters. So I run those numbers and get 4.70 milliliters of acid would need to be added. Number 2, which buffer system would have the greatest buffer capacity at, and it just says 9, it should say at a pH of 9. What we're looking for is a pKa value that is as close to 9 as we can get. So I'm going to go to the Ka table of values, and first I'm going to search for nitrophenol. And 4-nitrophenol has a pKa of 7. So that's a little far away to have a good buffer capacity at 9. Then I'm looking for hydroxylamine. There it is. And I have a pKa of 5.96. So again, that's pretty far away. I'd say that is a no-go. Then I'm looking for ammonia. And I get 9.24. Now that's pretty close. Ammonia is probably our answer. I'm just going to give it a click. And dimethylamine, I'm just going to double check. So dimethylamine has a pKa of 10.7. Ammonia is the closest. So it's going to have the greatest buffer capacity at a pH of 9.0. Number 3, we're going to calculate the pH of a 100 milliliter solution that contains 1 gram of imidazole and 1 gram of imidazole chloride. So I was setting this up before I realized I was not recording. So I'm going to find out how many moles of each of my compounds I have, and then we're going to use the Henderson-Hasselbalch equation. So I have 0.0146886 moles of imidazole, and for the imidazole chloride, the formula masses were given to us, so that makes it a little bit easier. 0.0095657, and that is imidazole chloride. Now, imidazole is a base, and because it is a base, this is the base, so this is going to be equivalent to the weak acid. So when we use the Henderson-Hasselbalch equation, again, pH is equal to pKa plus the log of whatever our base is over our protonated base. That's where we put our numbers. So that 0.014688 goes up here, and then the imidazole chloride value goes down here. But what about that pKa? Well, let's go back over to that Ka table because I realize you're going to need that pKa. And remember, when you see a pKa table, you're looking at the acid version. So when it is a base, it is the hydrogen added compound. So the pH here, 6.993. I'm sorry, yeah, the pKa, not the pH. And then we can just calculate. So 6.993 plus the log of this ratio, 46886, 95657. I get a pH value is 7.1. I get 7.9. I'd call that 7.18. So what is the pH of the solution? I guess that should be an if. If 2.30 milliliters of a 1.07 molar HClO4 are added to this solution. Well, now we need to play some buffer games. So we have our imidazole, and it's going to react with an acid in order to form our protonated imidazole. We know we have this amount. I just pushed it off the screen. So we have 0.0146886 amount of our imidazole. This is moles. And now we're adding this strong acid. When we add that strong acid, we're going to subtract the moles of our acid. So how many moles of acid are we adding? Well, the moles of the acid are going to be 0.00230 liters times the concentration, 1.07, because that is moles per liter. Liters cancel out. And I am left with moles, 0.07. So I am adding 0.002461 moles of acid. Now, when I do that, I am immediately making more of my conjugate acid here, 2,461, and it is equal to the moles of acid that are added. But I have to start with this value that I found above, moles. So now we can calculate our new moles and our new pH. So the pH is still going to be equal to 6.993 plus the log of a ratio, but now I have a new ratio. So this value here that I haven't calculated yet is going to go here, and this value is going to go here. So now I can calculate my new pH at 6.993 plus the log of my ratio, 0.012276 divided by 0.0120267. And I get my new pH is then 7.00. Now that makes sense, and it makes sense because when we add a strong acid, we expect that our pH will get lower. We'll push more towards the acid. My question number 4, calculate how many milliliters of a 0.1 molar HCl solution should be added to how many grams. So I need a volume of HCl, and I need a mass in grams of sodium acetate dihydrate, so NaOC 2H2O, to prepare 25 milliliters of a 0.1 molar buffer at a pH of 5. Well, again, Henderson-Hasselbalch is going to come into play here. So we're going to have our A- and our HA. When we have our sodium acetate, now sodium acetate is the conjugate base of acetic acid. So I'm going to come over here and look up acetic acid with a pKa of 4.757. I'm looking for a pH of 5.00. Sodium acetate is going to react with the hydrogen from the hydrochloric acid in order to form our acetic acid. Now, it's that acetic acid that has that pKa. So how many grams of this with how many milliliters of this in order to form 250 milliliters of a 0.1 mole per liter buffer? So I need to know how many moles of that buffer I need. So I do expect that you would be able to see that this is an acetate solution. This is an acetic acid and sodium acetate. So I'm told that I'm going to need 0.0250 moles of this acetate, and that's from the final 0.25 liters of 0.1. Now I'm told the formula mass of this, so I'm going to need 0.0250 moles of this sodium acetate, and I'm told it has a molar mass of 118.06 grams per mole. So I multiply those together. I'm going to need 2.95 grams of this sodium acetate. So there's one of my answers. Now, how much hydrogen do I need? Well, I'm going to take away some amount X. X is going to represent the moles of hydrogen. I'm going to force it to convert my sodium acetate into acetic acid. So I'm going to add log 0.025 minus X over X. So like the previous problem, I'm going to take my 5 minus 4.757. 0.243 is then going to be equal to the log of this ratio. Then I take the anti-log, or 10, to this being my exponent, and I get 1.7498. I have more digits. I'm just going to leave it in my calculator. And we are just working with algebra now. Multiply both sides by X. Add x to both sides, so 2.7498x equals 0.0250. Divide both sides by this 2.74 number, and I get x is 9.09 times 10 to the negative 3. Now again, what does x represent? Well, in this case, this is the moles of hydrogen that need to be added. I need to know, the question is, how many milliliters? So I'm going to take these moles and divide it by, essentially, the 1,000 milliliters, the concentration of my hydrochloric acid. So multiply that by 1,000, divide it by 0.1, and I get that I should be adding 90.9 milliliters of this hydrochloric acid. And the last question on this homework for me is, using complete sentences, explain how to prepare this amount of imidazole buffer at a pH of 7.5, starting with the imidazole hydrochloride. This is actually number 19 in this chapter in Harris's book. And what we're going to do is weigh out about 0.0125 moles of the imidazole hydrochloride. Now that value is obtained by multiplying these two numbers together. That gives us the moles. So that's moles of imidazole hydrochloride. We're going to dissolve that in about 400 milliliters of water. We're then going to adjust the pH to 7.50 with sodium hydroxide, because the pKa of this is less than that. It's 6.993. And that is shown right up here on our Ka table of values page. Then we will dilute up to a mark. We would be using volumetric glassware for this, and we would dilute up to the mark with more water. So we would definitely be using that sodium hydroxide. If we were to start with imidazole instead of the imidazole hydrochloride, then we would need the hydrochloric acid, because imidazole is a base, and we would need the hydrochloric acid to adjust the pH. So hopefully that helps to clarify any of the problems with this week's homework. If you have questions about the material or any of the problem solving, please reach out.